The same transformer revolution that's behind the ChatGPT's intelligence is now helping machines see the world almost like humans do. Stick along this video. We will talk about vision transformers mechanism, concepts visually, and hands-on code. With further ado, let's dive into the video. Vision transformers make real-world applications even more magical.
From automatic product tagging in e-commerce to autonomous self-driving cars. They also play a crucial role in satellite image analysis, segmenting buildings, rivers, and roads, providing detailed maps for better navigation. They power smart search when combined with language models. Example, type red car with a white stripe. In an image search, system retrieves the relevant images from the text queries better than the traditional metadata-based search. Under the hood, VLMs are powered by the vision transformers.
To understand why this is a leap forward, we need to look back at what came before, the CNN. Of course, CNNs are fast, they are parameter efficient, and they make clever use of inductive biases such as locality and the translation invariance. For example, if our target feature is a stop sign, CNN can detect it whether it's on the left side or on the right side or even on a hoodie or, or even on a billboard. But here is the issue. CNN focuses on the local regions using a small filter or windows. They detect features, but they don't understand how relevant that feature is based on the surrounding parts of the image. So even if a stop sign is just a part of an advertisement, CNN may still classify it as an actual traffic sign, a clear false positive. CNN filters only analyze a small local region of the image at a time, without considering what's happening in the rest of the scene, meaning they lack global context. But things took a big turn in 2021 when Google Research and the Brain team introduced a landmark paper, An Image is Worth 16 by 16 Words. This was the first vision transformer. It set a new state of art across the multiple benchmarks. Now let's dive into the architecture of the vision transformer. It begins with the patch embedding module, where the image is split into a patches and converted into embeddings. To preserve the spatial information, position embeddings are added as well. These embeddings are then passed into the series of layers, starting with the layer normalization, followed by the multi-edge self-attention, and then the finally MLP block. Let's break this down step by step. Let's take a bird image of size 256 by 256 with 3 channels. We'll look at the two ways to split it into patches. Method 1, manual patching. If we choose a patch size of 32 by 32, then along the 256 pixels width, we can fit 8 patches horizontally and another 8 vertically. This gives us a grid of patches across the image. So in total we get 64 patches. On top of that, we add one special patch called the class token. This is prepended to the sequence of patches. And why do we need it? For classification, we don't need prediction for every single patch. We just need one final label for the whole image, and the class token takes care of this by attending to all the other patches, gathering the informations and then serving as a final representation which is used for classification. To illustrate, consider patch number 12. This patch has a height and width of 32 pixels each, with 3 color channels, giving a total value of 3072, 32 by 32 by 3. Flattening this patch converts it into a vector of size 3072. We then feed this vector into a linear layer which outputs a 512 dimension vector. Here 512 represents the embedding dimension which can be adjusted based on the complexity of the task. Now all patches from class patch to patch 1, patch 2 and up to patch 64 all pass through the same linear layer producing a 512 embedding dimension vector for each. Interestingly, this linear layer shares the weight across all the patches and learns collectively from all of them. Since the input dimension is 3072 and the output dimension is 512, the weight matrix has a size of 3072 by 512 and there is one bias per output node, totaling to 512 biases. Along with this, we have a class token which is directly initialized to 512 dimension and they are also learnable. In addition to patch embeddings, we also add positional embeddings for all the patches. These embeddings have the same dimensions as the patch embedding and they are learnable parameters. We add positional embedding to the patch embeddings instead of concatenating. This is to inject the information about the spatial position of each patch, which helps the model to understand the relative positions of the patches in the image. Since there are 65 patches, including the class patch, the total number of learnable parameters for positional embedding is 65 by 512. Actual code in the repo implements a method too, called the convolutional patch embedding, also known as count2d patchify. Let's take the same bird image of size 256 by 256 and by 3. And to obtain the patch size of 32 by 32, We use a kernel size of 32 by 32, and also for non-overlapping patches, the stride is also set to 32 by 32. The image is then passed through a convolutional layer where the number of output channels is set equal to the embedding dimension. Next, the output dimension of the convolutional layer is computed using the given formula. In this case, the height and width reduced to 8 by 8 with number of channels equivalent to 512. This effectively produces a patches with spatial dimension of 1 by 1. Well, in the code level, we just use the PyTorch nn.con2d function and get patchified. The total number of parameters is computed using the formula. This calculation remains the same for both manual patch embedding as well as for the convolutional patch embedding. While the parameter size is identical in both the cases, convolutional patch embedding offers better GPU as well as the faster performance. In addition to patch embedding, we add positional embedding for all patches. These embeddings have the same dimensionality as a patch embedding and they are learnable parameters too. A special class patch is also included and it is initialized as 512 dimensional learnable vector. Since we have 65 patches in total, 64 patches plus one class patch, the total learnable parameters for positional embedding are 65 by 512. In code, we can achieve this by calling nn.parameters with shape 1, 1, 512, and that's our embedding dimension. For the positional embedding, we create nn.parameters with shape 1, 65, 512. Combining this in the code, in the init function we define the components required for the patch embedding, such as convolutional 2D layer for patching, one learnable class patch, and the positional embeddings. In the forward function, the input image flows step by step through the patch embedding pipeline. First, the image of shape 1 by 3 by 256 by 256 goes through the convolutional layer. Now this splits image into 8 by 8 patches, each having a 512 channel, giving an output of shape 1 by 512 by 8 by 8. Now we flatten these patches into vectors of 512 dimension, resulting in 64 patches total. Then we prepare the learnable class patch to represent the entire image. After concatenation, we get an embedding shape of 1 by 65 by 512. Finally, we add positional embedding to retain the spatial information, keeping the final shape same as 1 by 65 by 512. So far, we have covered patch and positional embeddings. Now let's dive into transformer encoder part, which includes layer normalization, multi-head attention, layer normalization again, and then the final MLP block. Layer normalization. Each patch is represented as 512 embedding dimension vector. Let's take patch 1 as an example. If we plot its value across the 512 dimensions, we observe that some features have very high activation while others are extremely low. Before normalization, the mean of these values is not typically centered around 0 and the variance is not close to 1. This imbalance can lead to unstable gradients and causing the training instability. Hence, we perform layer normalization and bring the vector mean centered around 0 and the variance close to 1. However, normalizing forces all features into a same distribution, which isn't the ideal case. In some cases, certain feature dimensions need amplification or shifted to highlight important information for the model. To achieve this, LayerNorm introduced two learnable parameter vectors, each of size 512 in this case. Gamma works like a knob that amplifies or reduces the individual feature dimensions, and beta works like a norm that shifts the baseline of each feature up or down. An important point, these gamma and beta parameters, they are shared across all the patches, meaning every patches uses the same set of scale and the shift in the given layer. This is the PyTorch code implementation of the layer norm. We will use it while constructing the transformer encoder layer class. Cool, now we reach the core intelligence of the transformer, the multi-head attention mechanism. In this layer, multiple attention heads are stacked in parallel, and each head receives a normalized output from the previous layer norm. Each head is essentially a self-attention module which relies on three key components: query, key, and value. These query, key, and value vectors work together to learn the relationship between the different patches, helping the model to understand which patch should focus on which other. We will explore this process more in detail next. Let's understand the query. To generate the query matrix, we take the LayerNorm output and multiply it with a learnable weight matrix of size 512 by 512. This operation transforms each patch embedding into a new representation that acts like a question, essentially asking, hey, which of the patches are relevant to me? Finally, a learnable bias vector of size 512 is added, resulting in complete query matrix. Similarly, To generate the key matrix, we take the LayerNorm output and multiply it with the learnable weight matrix of size 512 by 512. This transformation converts each patch embedding into a representation that is essentially revealing what information it holds. Example, patch could indicate I'm a part of an eye, or say I contain a bird's beak. Finally, a learnable bias vector is added, giving us the complete key matrix. Lastly, to generate the value matrix, we again take the layer norm output and multiply it with the learnable weight matrix of size 512 by 512. This transformation converts each patch embedding into a representation that carries the actual information the patch wants to contribute, essentially answering the question, what do I offer to others? For example, a patch may convey, I contain edge details of an eye, or say, I hold the textures of a bird's beak, and same like the query and key, a learnable bias vector is added, resulting in the complete value matrix. Let me introduce to an important hyperparameter called head dimension. It's defined by dividing embedding dimension by number of heads. This simply means that we split the embedding dimension across the multiple attention heads so that each head can focus on learning different relationship. This split happens for all the three modules: query, key, and value. Now we move to the next step where we transpose the key matrix and multiply it with the query matrix. Pay close attention here to the dimensions. For the each attention head, the query matrix has a shape of 65 by 64. Once we transpose the key, its shape becomes 64 by 65. This not only satisfies the matrix multiplication rule but also makes logical sense. Each patch's query is compared against all other paths key to understand how much attention should be given to each patch. Let's make this clearer with a simple example using just one head. Suppose the query matrix has a size of 3 by 2, meaning 3 patches and the embedding dimension of 2. The key matrix is also 3 by 2, but after transposing, it becomes 2 by 3. When we multiply the query 3 by 2 matrix with the transpose 2 by 3 matrix, the result is 3 by 3. This resulting matrix tells us how much each patch attends to every other patch. This matrix contains the raw attention score for every patch pair. Now we scale this score by dividing by the square root of the head dimension, which is 64 in this case. This step helps us to prevent like gradient exposure or to keep the attention values stable. After scaling, we apply a softmax function row-wise. This converts a raw score into probabilities, where the most relevant patches receive the highest attention weight and the rest relevant patches receives the lowest weights. Finally, because softmax is applied row-wise, the sum of each row becomes exactly 1. And that's how we calculate the attention score matrix for each head. After calculating the attention scores, the next step is to multiply these scores with the value matrix. The value matrix contains the detailed feature representations of each patch. By weighing the value matrix using the attention scores, we obtain the final context vector. This vector represents the refined information for each patch, capturing what's most relevant based on the attention scores. Next, we take the context matrix and reconstruct it back into patch embeddings. This is done by concatenating the outputs from all the attention heads and then projecting them back to the original embedding dimension. Additionally, we add a residual connection from the original patch embeddings. This skip connection ensures better gradient flow during the training and makes the network more stable and efficient. After the skip connection, the output is passed through a layer normalization step. We already discussed how this works, and next is the normalized output goes into the MLP block, also known as the feed forward network. Here the hidden feature dimension is set to 2048, which is typically 4 times larger than the embedding dimension. After the MLP processes the data, we apply another skip connection to preserve the original information and also to ensure better gradient flow. With this step, the entire sequence completes one transformer layer. Moving further, the output from the transformer layer is passed as input to the next layer, and this process continues through all the layers in the network. Finally, the output from the last layer is sent to a global linear norm and then to the linear layer where the actual classification takes place. And this entire stacked structure together forms as a complete transformer used inside the vision transformer.
Let's now understand multi-head attention more conceptually. Imagine we have a matchmaking hall, and this hall can be thought of as a patch embedding matrix. Here, each patch can be imagined as a prospective groom or bride. The goal of the whole process is to find out, is there even one highly compatible couple within this matchmaking hall? Now, as we know, the embedding dimension is split into a number of heads, 8 in this case. We can think of these 8 heads as 8 specialized matchmakers.
Whenever two people meet for a prospective marriage, there's a lot going on in their mind. Looking at the prospective alliance from the multiple perspectives, like education background, about their qualification, how the person is raised, will they share the last slice of the pizza? Do they have the fitness goal? Or their best cardio is reaching fridge at night 2 a.m.? How smart they look, actions, personality, they believe towards a spiritual path, and of course, financial knowledge and stability. Does he knows to read the portfolio, Bitcoin strategy? Just kidding. But guess what? From the self attention perspective, this is exactly what multi heads do. Each head focuses on one specific aspect, just like each thoughts in our mind. This helps to decide whether it's a match made in the heaven or just a left swipe situation. Like we saw, each head takes care of specific aspect. Let's choose career head and deep dive more on the components of this.
To keep the things simple, let's select 3 patches, one bride and the other 2 grooms. When the bride patch acts as a query, it represents her requirements and searching for the most relevant matches among the other patches. For example, this bride is looking for a groom who is ambitious and aiming for a leadership role in his career. Now, when the same patch or the bride takes the role of a key, it represents the features or attributes that defines its own identity at the surface level. Similarly, the other 2 groom also represent their own key informations. Probably the groom 1 may say, I'm a school teacher and I love teaching kids. And the groom 2 may say, I'm currently a manager and I'm looking forward into my leadership roles like a director level. Next, we calculate the attention score between the bride, that's a query, and the 2 grooms, which are keys. From this, we find that the first groom is less compatible compared to the second groom from the bride's preferences. Once the attention scores are computed, we then multiply them with the value component. When in the value component, bride's patch provides more detailed information about her career. For example, well, I'm a founder of an health tech startup with 10,000 users and I'm planning to scale even further. Similarly, the other 2 grooms also share their detailed information about their career through the value matrix. Well, in this way, each head develops its own context based on its specific task. The personality head focuses on how comfortable the personalities are, and similarly, other head captures different aspects of the relationship. Once all the heads compute the output, this combined information is passed to the layer normalization and the MLP layer. Together, these components complete one transformer layer. And in the vision transformer, we can have multiple such layers, say 4 layers, where information is progressively refined as it flows through. Finally, after the last transformer layer, we focus on the class patch, which acts as a summary representation of the entire matchmaking hall. The summary patch is then passed into a linear layer classification, which decides whether the hall has at least one potential match or not.
Now let's apply the previous concept learning to a bird image scenario. After patchifying the image, we apply the layer norm and total we have 64 patches along with that one class patch with the embedding dimension as 512.
After splitting each embedding dimensions to number of heads, say 8 heads, each head processes a different part of the information. For our understanding, we can imagine one head focusing on shapes, another on the structural details, another on the colors, and so on. However, it's important to note that these head level tasks are not predefined. The model self learns what each head should focus on to minimize the overall loss, and this depends upon the task. Let's deep dive further. Let's select a few patches and understand how the query key value works in this case. Take a patch near the bird's neck. For the texture head, when this patch acts as a query, it tries to search for other patches that are texturally similar or helps it to complete its local pattern. Now, when the same neck patch plays the role of the key, it represents high-level information about itself. For example, its fine-grained feature patterns or local textural features in the neck area. Consider another patch from the leaves area. As a key, it encodes branch strokes, leaf textures, and more. A wing patch would represent feature textures while the background patch captures smooth background patterns. Using this query key relationship, the model calculates attention scores between the neck patch and the all other patches. For the texture head, the wing patch is likely will receive a higher attention score compared to the leaf or the background patches, since their textures are more closely related or they belong to the part of the body. Finally, these attention scores are multiplied with the value vector, which carries detailed patch information, allowing the model to integrate context-aware representation for each patch. This way, each attention head develops its own context based on its specific task. Once all the heads compute their output, this combined information is passed through layer normalization and the MLP layer. Together, these components completes one transformer layer. Similarly, it's passed on to the next layer after the last transformer layer. We focus on the class patch, which acts as a summary representation of entire image, and it's passed on to the next linear classification layer, which decides whether the subject is bird, animal, car, or whatever is defined. As we move to the code part, below visual shows us the whole flow. Inside the init function of the class vision transformer, we define the patch embedding, which we saw earlier, and then we have an encoder, which is a stack of transformer layers. In this case, it's 4. Later we use the for loop and stack this transformer encoder layer using the sequential layer, and then one LayerNorm followed by the linear classification layer. In the forward function, the flow starts from passing an image of shape 3 by 256 by 256. Batch size is 1 for the example, and then we pass it to the patch embedding, resulting us in 1 by 65 by 512. Later we pass it to the layers of transformer, which are encoder layers, resulting us in the shape 65 by 512, and then one layer normalization for better training stability. And then we fetch the first patch, which is a class patch of the size 1 by 512, and this is passed to the classification linear layer. Now we will see inside the transformer encoder layer code in detail before we move to the code execution. So the single transformer encoder layer, it consists of LayerNorm. We just need to provide the embedding dimension as an argument while using the torch library. And we also have the easy way of defining the multi-head attention using the library. It just needs the arguments as embedding dimension, number of heads, and the dropout rate. Followed by this, we have the LayerNorm as well as the MLP layer. What's the MLP layer? Let's say inside the MLP class. MLP class consists of 2 fully connected layers as shown in the right bottom visual. In the forward pass, input is passed to the first linear layer using the dropout and the GALO activation function, just for getting the smooth and differentiable gating, basically helping the gradient flow. And this output is again passed to the second linear layer inside the dropout layer, and this also helps to avoid the overfitting. So overall, we maintain the same shape before and after the MLP. Now coming back to the transformer layer, in the forward loop, we first perform the multi-head attention pass by giving 3 additional arguments: query input, key input, and the vector input, where all are covered by the layer normalization. Pay attention here, we also add the input to this as a residual connection. Next, this output is passed to the MLP layer, and again the input is added along as a residual connection. Now this whole block is a single transformer layer.
Cool. Now I'm using an Kaggle's notebook, and the first step is that we go to the settings and we turn on the accelerator. Because Kaggle offers a free GPU as, I'm gonna use the GPU P100 or the T4 because I'll get 30 free hours in this, and it's for the small to medium size, it works pretty well. If you're working with a very larger model, you could go with the TPU, and if it's a tensor framework, it's well enhanced. So with that being said, we'll import all the necessary libraries. We would need the torch and the torch vision libraries because we want to load the data and for the optimizer purpose as well as for the transforms where the augmentations and all we apply it. Next, we set the device to CUDA. The next part is that setting the values for the random seed, because every time when we run this code, we want to have the same initialization happening. So then we use the image size of 256 by 256. This resolution is large enough for the model to capture the scene level context. And then we use a patch size of 32, which will give 64 patches for the given image size. Along with that, we also have the class token. That's a manageable patch size while still letting the attention mechanism show how different parts of the scene interact globally. Next part is that we have the class patch embedding, the architecture part, and then the MLP as well as the transformer encoder layer. All these things we put it together into the class vision transformer. We did see about this much more detail in the previous part of the video. Later, we'll also instantiate the model. So here we use the PyTorch transform to define the pre-processing operations to our images. For training, we resize the images to fixed size of 256 by 256, and then the random flips, color changes,
to stimulate the varieties and then convert it to the tensor as well as normalize it so that the model can learn effectively. On the validation side, we just resize it and convert to tensor and normalize it. Okay, now it's time to add the dataset. Here we'll use the places 365. Go to the input and click on the add input, and again on the datasets, search for places 365. So select the one which shows up like this. It's a 25 GB dataset, it's huge and it has around 1.8 million images. Click on the add button. For me, I have just already added this. One interesting thing about the places 365 dataset is that classification depends upon the entire scene. To recognize whether it's a classroom, kitchen or beach, the model has to understand completely the global context across the image. So this makes places 365 a good fit for us to demonstrate the power of vision transformer. Now we will use a subset of places 365. Here we'll use only the first 25 classes. The reason is, firstly, the data itself is huge and we are limited by the session limit of just 12 hours from Kaggle. So we'll use filtering of images, and after filtering the 25 classes, well, on the training side we have 124,000 images. That roughly translates to 5,000 images per class. And on the validation side, we just have 2,500 images. In practice, when you build a custom dataset, you usually keep at least like 10 to 20% aside for validation. But this is a places 365, a benchmark dataset with the fixed splits. So we are just sticking with the official available validation dataset. And our goal here is to see that how vision transformers capture the global context across the entire image. So after that, we use the data loaders to split them into a batches with batch size as 512 as defined in our parameters. Now after loading the data, here we could see like we have training side 243 batches with each batch size as 512, and on the testing side we just have 5 batches of 512. Next step is that we define the cross entropy, the loss function. Since it's a multi-class, we'll use the cross entropy here. And then we define the optimizer. We use the upgraded version of Adams, that is Adam W. Here what happens is the weight decay is decoupled from the gradients updates, and it's quite commonly used across the VAT models for their stableness. And in the next step, we define the training function. We pass the model, training dataset, optimizer and the loss function. In the for loop, we take the input and the GT and we set it to the GPU. Optimizer.0grad helps us to reset the gradients. After every pass, we need to reset this value. In the forward pass, we take the input and give it to the model, run the inference and get the output. Later, using this loss, calculate the gradient and apply with respect to all the parameters. And the next step is the total loss. So we are running the for loop. For every batch's loss, we accumulate this so that we can calculate the average loss for that given epoch. Well, in this line, we check for the accuracy. For the given batch, how many images did the model correctly predict the class against the GT? So this helps to identify the accuracy, and this one is for checking the magnitude of error. Next step is that we move to defining an evaluate function. Here we pass the model and the validation data. So model is set to an eval mode, and similar like the training, we run the for loop for the validation data loader. In the forward pass of the model, we pass the input, we get the output and we check for the accuracy. Next we import this TKDM library. Takadam, the word in Arabic meaning progress bar. Well, this is where exactly the training is happening. We run a for loop for the given epochs, and inside this for loop we call the train function. We pass the model and training dataset and we calculate the training loss for the epoch as well as the training accuracy. Right after this, using the same model, we'll also check it on the test data using this evaluate function. We'll collect both the informations and append it to our list, because we want to see how the model progress over the epochs and does the model have a good learning or not. Followed by that, we'll also plot the results against the epochs and see that how is the test and the training accuracy is improving over the epochs. For now, what I'll do is that I'll kick off the training. It'll take a lot of hours to train. I'll let it run for some time, and once the training is done, I'll get back. Cool. Now the training is done. As the training progresses, we could see that the losses are decreasing and the accuracy is increasing steadily. We can see that the model is actually learning, and early on the epochs, the accuracy is low, but as the time it reaches the 10th epoch, it is climbing past 60% for the pure scratch training.
Of course, we are just using the 25 classes. We can still improve the results by using techniques like cosine annealing or increasing the batch size or also introducing more augmentations on our training side. However, the model is like generalized for us to visualize a meaningful attention map. We'll write a function where we pass 12 random images on the validation data and we see how does the model predict on them. Many samples like airplane cabin, amphitheater, aquarium are predicted correctly, showing the model is learning class semantics. But when we look at the class alley and apartment building outdoor, it needs more discriminative power. Of course, it's scratch training.
Finally, we will view the attention maps and see where the model focuses on. To do that, in this function, we attach the hooks to the model's attention layer to capture their attention maps during the forward pass. I have taken two classes which look similarly. One is an art gallery, another one is an art school. I have taken the art gallery and we will view how does the attention map looks like for this image. So in this cell, we'll be plotting the results for all the 6 attention layers. As we could see, on the layer 1, the focus is broad and it's also like diffuse. In the layer 2, the attention begins to narrowing towards the paintings and the human figures. As we progress to the layer 6, the model has a broader, balanced focus combining the paintings, people, and the gallery, helping it to build the global context. Similarly, we'll also check it for the art school. How does it look? Here we could see that in the layer 2, we could see it's began to concentrate on key objects like the hands and then the tools and the yellow paper more. As it progress over the layers, in the layer 6, the highest level abstraction we could see, the model is emphasizing on the person and the paper, tools, hand, helping it to understand like the relevant clues that it is an art school class and showing that how the essence of vision transformer interprets the scenes.
Well, that's a wrap. We are building amazing stuff together. Stay tuned. Till next time, happy coding.